everybody, and welcome back to Linear Algebra with me. Remember last time we left off, I had promised to tell you how determinants were going to help us with determining whether or not A was invertible or not. And that's what we're going to finally get to today. I'm going to answer that question. But before we can answer the question, I've got another question. How do row reductions affect determinants? If we can answer that, we can talk about the invertibility of A, because we know invertibility of A is related to A having a unique solution, which we discover by row reductions. So let's figure out how row reductions are changing or not changing determinants. We're going to start off with our 2 by 2 matrix. We've got A equals 2, 5, 2, 4, and we're going to find the determinant. So determinant of A will be equal to, we take 2 and we multiply across to 4, and then we subtract multiplying backwards, so 2 to 5. Okay, so that's going to be 8 minus 10, negative 2. Now we're going to put A in reduced echelon form, and we're going to find his determinant and just check out what it's doing. So we've got 2, 5, 2, 4, and you can't really subtract these to get a 1, but you can multiply the bottom row by a half, and so I'm going to do that in order to get a 1 in my first entry. Okay, and then I'm going to switch my rows so that my 1 is sitting where I want him to sit. And now this should feel like comfortable Gaussian elimination. Okay, well, let's see, we'll say that's B. It's pretty uninteresting. The determinant is just 1. Okay, so the determinant definitely changed. How did it change, though? When was it changing? When was it doing things? Was it related to the changes that we made? My intuition says that A is row equivalent to B, so there must be some logical way to connect the determinant of A to the determinant of B. So what we're going to do is we're going to slow this down, and what we're going to do is examine the determinant at each of these steps. So these are just the steps that I had on the previous page. So let's remember determinant of A was negative 2. And first thing I did was I did 1/2 times row 2. So let's take the determinant of this matrix. So that's going to be a 2 times 2 minus a 1 times 5. And that's going to be negative 1. Okay, so what has happened is this is half of what it was. So then we're kind of like, okay, that kind of makes sense. We divided one of the rows in half, and that made our determinant half of what it was. Okay, that's pretty logical. And then next we switch some rows. So now we have 1 times 5 minus 2 times 2. So that is now a positive 1. So this flipped our sign from negative to positive. And again, that's very sensible because you can see that these rows right here switched, they're backwards from before because we did a row switch. And that means where before we would come up and have a minus 1 times 5, now when we come up, it's the minus 2 times 2. And you're like, okay, so yeah, that would totally have a changed sign in the determinant. Now let's see what a row change or adding rows together is going to do. So now we've got 1 times 1 minus is 0, so that's just 1. and then a 1 times 1 minus a 0 again, so that's still 1. So that had no change at all from before. Okay. And to me that kind of makes sense because like when we multiply by a scalar on a particular row, you are like changing the matrix from the outside. And same with the row switch. It's like, okay, I have arbitrarily like taken these things and moved them again from the outside. But then when you do steps like this one, you're like, oh, that's all inside the matrix. That's just the matrix talking to itself. And I feel like I can justify, oh yeah, like those ones wouldn't change it. That's just it talking to itself. This is me coming in and playing God with the matrix when I come in and do those operations though. And so yeah, I can see why that would change the determinant. Okay, so if we follow this string through, we've got the determinant of A, which was the very first result, was 2 times the determinant after doing this 1/2 row operation. And then we did the row switch, which is this one right here. And so now we have a negative sign that came in, and then after that, they didn't change at all. So then the determinant of 1, 1 was just 1. And there we go. The determinant was indeed -2. Pretty cool. So we've got a theorem about that, in fact. So theorem 3, number 1, if one row is multiplied by k to produce a row equivalent matrix B, then this is exactly what happened. The determinant is going to be the opposite of what you had. So we did a 1/2, which means we needed to multiply by a 2. If we had multiplied by a 2, then we would have to divide the determinant by a 1/2. So we're like undoing whatever we did to our row. And then if 2 rows interchange to produce the row equivalent matrix B, then we have a sign switch on our determinants. And we already talked about why that made sense. And then if a multiple of one row of A is added to another row to produce the row equivalent matrix B, then the determinants are equal. So why exactly is that useful? Do you remember we had a theorem about triangular matrices? I think it was at the end of the last lecture. Triangular matrices have easy determinant. I can't talk and write. Determinants. Right? Because you just take the product along the diagonal and you're done. So what if we used a combination of doing some row reductions and then we took the determinant to try and make things a little bit easier? Would that help? Well, let's try and do that for example 3. Once again, I see this row and I'm like, oh, if I just multiply that by a 1/2, then I can have that easy 1 in that first entry. So -3, -6, -8, 0 to 5, 2, 4, 6. And then subtle difference. I have square brackets on the matrix, which would have like a foot and a head. But right here, I've just written bars. This is lazy for determinant, if you don't want to write out the word determinant, which I don't. Could you guess that? So if we do 1/2 row 3, that's going to go to 2 times the determinant of the resulting matrix, which is this. And then we're going to do a row switch. So row 3, row 1. And so then carry that 2. And it's got a negative on it now. So 1, 2, 3, 5, 3, 6. And then let's try and get rid of the 3 here. So that's going to be row 3 plus 3, row 1. And that doesn't do anything. So 1, 2, 3, 0, 2, 5, 0, 0, 1. And then the determinant of that is really easy. That's just 1 times 2 times 1. There we go. Determinant, -4. I'm like, Gracie, that didn't really like save me a whole lot of time. I'm like, I guess not. Sometimes it will be more effective than in others. And for computers, this technically takes fewer steps, and so it would make like a computer program more efficient, even if it's not necessarily more efficient for us humans. But what it does give us is something interesting about when A has a solution. So like remember, if you've got a triangle matrix, then you only care about the entries on the main diagonal. So if we only care about the entries on the main diagonal, if there were to be like a 0 on our main diagonal, our determinant would be 0. What else does that mean? Like going back to day 1, what else would having a 0 on that diagonal mean? Think number of solutions. Maybe like, here, I'm gonna do, I can give myself a little bit of space to write. I'm gonna write in black. I'm gonna say, recall that if A is invertible, aka it has a unique solution, then A is row equivalent to the identity matrix. So running back to determinants, but the determinant of the identity matrix is not going to be 0 ever, because it's just going to be 1 times 1 times 1 across the diagonal. But we also know that the determinant of A is just going to be some number times the determinant of I based on what row reductions we did. So that brings us to how we're going to tie determinants in with invertible matrices. Theorem 4, it's just an extension of the invertible matrix theorem. A square matrix is invertible if and only if the determinant of A is not equal to 1 or not equal to 0, because the determinant of the identity matrix is 1, and the only thing that's going to change is multiplying it by some scalar that's not going to be 0, because you can't like multiply one of your rows by 0. And so it can't be 0 on the outside. You can just do whatever scalar you multiplied your rows by and flipping signs. That's it. That's your only choices. So it's not going to be 0 for the an invertible matrix. So that was what I promised you guys last time. We are now there. But now we've talked about row operations. What about other things? What about transpose? Transpose is a thing that we've done with the matrix. What happens when we do that? That's theorem 5. Determinant of A is equal to the determinant of the transpose of A. And this is a tedious proof with induction, which requires like 381. And I can't assume that you guys have had 381. But I am going to give you a peek at why it works. Suppose we've got our matrix A. If we want to take the determinant of A, remember we do A times, and then we cross out his column and row, and we do the determinant of what's left over. So EI minus HF. And then we do, oh yeah, also remember the plus minus plus, the checkered board. Next we have minus B. We cross out his stuff, and then di minus gf. And then we have c dh minus ge. Okay, so what about if we do the transpose now? Remember, so you've got the checkered going this way, but we can use cofactor expansion, and we can do the checkered pattern going down, and now we can expand down along the column instead of the top row. So let's try that instead this time. So we've got A, then we cross out his row and column. So that's EH minus FI. No, I'm just, okay. It's like, that's wrong. That's wrong. Are you guys paying attention? Are you awake? Did you catch that? Okay, there we go. And then we go down along the column. So the next one we have is B. So we cross out his row and column. So minus B. And then we do the product or the determinant of the leftover matrix. So D times I minus F times G. And then the very last one is C plus C DH minus EG, which you'll notice matches. The only thing that's backwards is like the F times H, and that's fine because F times H and H times F, those are the same. Same thing for here. You got your G and F are backwards and the G and E are backwards, and those are all totally fine. This is exactly the same thing. So it's not exactly a proof, but I feel like seeing this is kind of like, oh yeah, I can buy that. Sure, I'll trust you. Okay. And then we've got a couple of more properties that we can look at. We can do like product of matrices. So the determinant of A times B is the same thing as doing the determinant of A times the determinant of B. And you guys actually saw an example of that happening on your worksheet yesterday, where I had you calculate the determinant of A, determinant of B, and then I had you multiply them together and take that determinant, and you guys should have found, hopefully, that the determinants were equal. If they weren't equal, algebra got messed up. Big warning, you saw this on your worksheet also yesterday. Determinant of A plus determinant of B does not equal determinant of A plus B. You should have seen that on the worksheet. I had you find this guy and I had you find this guy, and they were not the same. Definitely. I made sure that I found an example that didn't somehow, most of the time it's not going to be the same. Like if you have B as the zero matrix, things are going to end up being the same. But yeah, you should have already seen that this fails. And the very last is if A is invertible, then the determinant of A inverse is going to be 1 over the determinant of A, which the determinant of A can't be 0 because we already have a theorem. A is invertible, then the determinant is not 0. And so, yeah, I can see that working out. And it's not that bad of a proof. And it's so not that bad of a proof that I've left it for you guys for your worksheet today. So I'll see you later today, and we will work through that proof specifically and a couple of other problems. Bye.